Hello everyone, welcome to another episode from Chedexcel. Today I am going to talk to you about identification tests we have in chemistry. So today mainly I am focusing on Unit 3 paper, Edexcel IAL Unit 3 paper, all the identification we get in Unit 3 paper, but you know that Unit 6 paper also you need almost all the Unit 3 identification. So I'm going to talk about identification test, and most of the identification test is useful for the IGCSE as well. And in generally chemistry, if you are doing any sort of examinations, the identification tests for the cations, anions, gases are really important. So we'll see what are the main identification tests we can do to identify different types of substances. Right. The very first one I'm going to talk about is identification of positive ions. In fact, we call them as cations. I put a separate video on practical how we can do them practically. Today we mainly focus on the basic theory part. So identification of cations, mainly we have the flame test to do. So flame test is a common method we use to identify most of the cations. So flame test, how we do the flame test, those steps have asked both Unit 3 and Unit 6 papers. How we carry out the flame test, you have to take a platinum or nichrome wire, dip it in concentrated HCl, place it into the test sample, hold it into the non-luminous part of the Bunsen flame. So those are the common 4 steps we can write. Now sometimes we take the platinum wire, dip it in HCl, hold it to the non-luminous part, again dip it in HCl, that is to clean the platinum wire. Assuming platinum wire is clean, we can just get it, dip it in HCl, dip it in the test sample, and then we can place it to the non-luminous part of the Bunsen flame. Right. Why do we need platinum or nichrome? Importance. Why? One reason is they are unreactive. The second reason is they have very high melting point. Why do we need HCl? We can't use nitric or sulfuric for this. Why do we need HCl? Because we say chlorides are highly volatile. That's the reason why we use HCl. Right. So I'm not going to talk about how flame colors are obtained. We'll be talking them in Unit 2 theory. Colors, how do we identify? There are a few colors that you have to remember. So group 1, lithium plus, sodium plus, potassium plus, cesium plus. Cesium is not that important. Then group 2 we have beryllium 2, calcium 2 plus, strontium 2 plus, barium 2 plus, and sometimes they can ask copper 2 plus. Color wise, lithium is dark blue, dark red or deep red color. Sodium is yellow, potassium is a lilac color. Cesium has blue color, but they haven't asked it that much here. Calcium is a orange, or you can say brick red. Strontium 2 plus is crimson red. Barium 2 plus is apple green. Copper 2 plus is blue green color. Now remember, when they ask in the papers a red flame is seen, we never consider it as calcium, because calcium is orangish color. When it says it's red, we always assume either it is a lithium or strontium. And when you ask to write the cation, remember you have to write the cation. You can't just write lithium. Lithium doesn't give a color. Lithium plus gives the color. So this is the identification of cations using the flame test. These are the colors. Right. Next cation we commonly get to identification is ammonium, NH4 plus. Right. How do we identify ammonium in a flame test? What you have to do is, to identify ammonium, you have to add sodium hydroxide. When you add sodium hydroxide into ammonium, you get ammonia gas. So we'll see how we can identify the ammonia gas later. But ammonia gas is given. So ammonia can turn red litmus to blue color. So that is a very common test. We can identify the ammonia gas, because in your syllabus or generally in chemistry, ammonia is the only gas that turn red litmus to blue color. So from that we can identify ammonia. Remember, ammonia is obtained when by adding sodium hydroxide into ammonium. So that is a test to identify ammonium cation. When you add sodium hydroxide into ammonium, it gives ammonia gas NH3. Remember, it's ammonia NH3, ammonium NH4+. The formula is really important. Right, ammonia gas is given which turns red litmus into blue. We have another test, I'll tell it later. Right, so those are the common cations. Other than that, we have acid H+. There are no indicators, there are no any reactants we can use to identify H+. H+ can only identify using an indicator. H+ is there with phenolphthalein. Phenolphthalein is colorless. Then with methyl orange, it is red color. And if we add a carbonate into this, we will get effervescence. So when you see effervescence by adding a carbonate, we can say that is because of it is acidic. So those are common tests we use to identify H+ ions, but they have rarely asked about that as well. Right. So that is the main cations they ask us in Unit 3, identification of the cations from the flame test and ammonium, and finally H+. Right. So that is how we identify the cations present in a sample. Right. Those are the common tests for the cations. Right. Then I am moving to the gases, because many gases are there. First thing is, from O level onwards, how to identify oxygen. Oxygen gives a glowing splint relights. So you have to test with the glowing splint relights. That's for oxygen. Then what about hydrogen? We use a burning splint. Squeaky pop sound is given with the hydrogen. So when a gas is held, or when a burning splint is held towards the gas, we see a squeaky pop sound. Like normally it comes like sound. Right? That's how the sound comes. That's a hydrogen. So what happened there? Hydrogen reacts with oxygen in the atmosphere to produce water. The reaction is highly exothermic. That's why we get that squeaky pop sound when it burned in air. The next thing is how to identify carbon dioxide gas. So to identify carbon dioxide, what we do is we have to pass the gas. Normally don't say add the gas. We can't add gases. You have to pass the gas through lime water. Lime water means aqueous calcium hydroxide. It produces calcium carbonate solid and and water. So calcium carbonate gives a milky white precipitate. That's how we identify carbon dioxide gases, right? Carbon dioxide gas. Then ammonia. How to identify ammonia gas? As I told you earlier, it will turn red litmus into blue color. Ammonia, red litmus to blue color. And then if we held a lid of concentrated HCl, it will give a dense white smoke. What happened there is ammonia reacts with HCl to produce ammonium chloride. So from there you can identify ammonia gas. It gives a dense white smoke with HCl. So what you do is you get a lid of concentrated HCl and we head it towards the gas. So it will give a dense white smoke. So that is how ammonium chloride is a white solid. Ammonia, right? So that is for ammonia. Other than that, other common gases we have is sulfur dioxide. They don't ask it that much. Sulfur dioxide has a pungent smell and it is acidic and it has some kind of bleaching properties as well. How to identify chlorine gas, Cl2? To identify chlorine gas, what we have to do is, chlorine has bleaching properties. So if we held or if we test with the damp blue litmus paper, chlorine will first turn it into a red color and then it will get bleaches. So that's how we identify chlorine gas. Chlorine will turn blue litmus to red and it gets bleaches. That's how we identify chlorine. Other than that, H2S we have. H2S has a characteristic rotten egg smell, a very bad smell. That is only due to the H2S. So H2S can identify using the rotten egg smell. Other than that, we have nitrogen dioxide, which is a brown color gas. The two brown color gases you have is NO2 and Br2. NO2 is mainly obtained from thermal decomposition. Of most of the nitrates, especially all group 2 nitrates, thermally decomposed to give nitrogen dioxide, which is brown vapor. Bromine is also a brown gas, but bromine is only obtained when we test for bromide. I'll tell that as well later. So those are the common gases we have to identify. Other than that, we have iodine. Iodine has a purple color, right? Purple vapor. So only purple vapor gas is iodine, right? So that's how we identify the common gases. Those are the common things they ask for Unit 3 paper, right? So quickly we'll move to the identification of negative ions. So we call them as anions. So how do we identify anions? One thing is very common anion is carbonate, CO3 minus, or hydrogen carbonate. So what happens is when you add an acid, you'll see effervescence. You see a gas bubbles comes off, which is carbon dioxide. Then we have to pass through that, pass the carbon dioxide to lime water to identify, to confirm whether it's a carbon dioxide. So what happened here is, this is the ionic equation. This is very common ionic equation. They ask carbonate reacts with acid to produce carbon dioxide gas, H2O liquid. I have taught you how to write the ionic equation in Unit 1. So this is how we write the ionic equation for the carbonate with acids. Carbonate and hydrogen carbonate both give the same observation. For you guys, I don't think that they would ask how to distinguish carbonate and hydrogen carbonate. Usually they won't ask that one, right? Other than that, very common one is sulphate. How to test for the sulphates? We had acid and barium chloride. So when sulphate SO4 minus reacts with barium 2 plus, it gives a white precipitate of barium sulphate. From that you can identify the sulphate ions. This is also a very common ionic equation they ask. A test with barium chloride. We use that to identify sulphate ions. It gives a white precipitate that doesn't dissolve in acids, right? So that is for the sulphates. Then what happens? Now sometimes we use the same reaction to identify barium 2 plus ions as well. Other than the flame test, we can use this test to confirm that it is barium sulphate, because barium sulphate doesn't dissolve in acids, right? So that is for the sulphates. Then we have anions, chloride, bromide and iodide. This is very common things they ask. There we have two types, right? Let's say aqueous solution of chloride, bromide and iodide. If you are going to identify aqueous solutions of chloride, bromide and iodide, what we do is we are using silver nitrate. So when silver nitrate is added into a chloride, it gives AgCl, which is a white precipitate. If it is a bromide ion, it gives a cream precipitate. And iodide ion, it gives Agi, which is a yellow precipitate, right? It gives a white precipitate, cream precipitate and yellow precipitate. AgCl, this one dissolves in dilute ammonia. Silver chloride completely dissolves in diluted ammonia. AgBr, this one dissolves in concentrated ammonia. Now when you have concentrated ammonia, at first we can't really say whether it's a chloride or a bromide, because AgCl can also dissolve in concentrated ammonia. It dissolves in dilute ammonia as well, so obviously it dissolves in concentrated ammonia. Agi, this one, that does not dissolve. So that's the common thing with main difference with silver iodide. It doesn't dissolve in concentrated or diluted ammonia. None of these precipitate dissolves in acids, right? So if you add all three into HCl, no change. HClO nitric, let's say. Nothing would happen if you add these precipitate into the acid. It dissolves in dilute ammonia, AgCl, concentrated ammonia, AgBr, but none of them, even including AgI, they don't dissolve in acids. When AgCl and AgBr, only these two, when we expose them into air or expose into sunlight, what happens is the precipitate turns darker color because it produces silver when we expose them into sunlight. So AgCl, when we expose into sunlight, it turns darker color. AgBr, the precipitate, if we expose into sunlight, it turns darker color. That thing haven't asked recently. Recently means in 2023 they haven't asked, but they can ask it again, right? So those are the common way we can identify aqueous chloride ions, bromide and iodide, mainly using silver nitrate, right? The final way we have is identification of solid iodides. So solid halide, solid chloride, solid bromide and solid iodide. So solid chloride, bromide, iodide. So I'm not going to write in any equation or something. We are using sulfuric acid, concentrated sulfuric for this. With chloride, you can't get anything that much difference. HCl and HSO4 minus is formed. I'm not writing the balance reaction. HCl has a steamy fumes, we say, or misty fumes, right? When it has a bromide, it reacts with sulfuric to produce common observation is Br2 and sulfur dioxide. Bromine is a brown vapor. Sulfur dioxide, we say it has a pungent smell, right? That's how what happens when you add solid bromide into a sulfuric. Then solid iodide into a sulfuric. You get iodine, that is a grey-black solid because normally you get it as a solid state. H2S gas, which has a rotten egg smell. And we get sulfur precipitate, and sulfur precipitate as a yellow color. So those are the three common observations when you test solid halides with concentrated sulfuric acid, right? So those are for the aqueous and solid iodide, chloride, bromide and iodide, and those are the common anions they ask. They normally don't ask you to how to test for the nitrates, how to test for the chromates. They won't ask those stuff. Right. So the last one, we have to identify some compounds. One thing is identification of water. It's a very common one they have asked. To identify water, what do you add? Right. Water, we have to test chemically and physically. To identify water chemically, we add anhydrous copper sulfate that will turn from white to blue. Or we have another one called anhydrous cobalt chloride or cobalt nitrate that will turn from blue to pink. That will turn from blue to pink. That's how we identify. Physically, we identify water by measuring its boiling point. Water boils at 100 degrees, or we can measure at freezing point. Water freeze at 0 Celsius. Right. That's how we identify water. Now we have some right. Those are the identification of common things. If we move to the identification of organic compounds, in S level we have alkanes, alkenes, halageno alkanes and alcohols, a little bit of aldehydes and ketones and carboxylic acids. So we'll see how we can identify those stuff. Chemically we can't identify alkanes. So we'll move to the alkenes. To identify alkenes, we can add bromine, liquid bromine. So if we have alkene, there are three tests. Br2 liquid, color change would be brown to colorless, right? Brown to colorless. Then bromine aqueous is yellow to colorless. Then we can add acidic KMnO4, potassium manganate 7. It is pink to colorless, right? Brown to colorless, yellow to colorless, pink to colorless. So what happens is with bromine you get 2 Br atoms, right? Instead of a double bond breaks, you get 2 Br atoms. Yellow to colorless is you get a Br and OH I'll explain these reaction in details later in video. These are just two identification tests. Pink to colors, you get two OH group instead of the double bond. So if let's say if I have a CH3, CH3, HH, here CH3, CH3, HH. This one is when you have bromine water, normally bromine water the one with more hydrogen. So here bromine H, H, OH, CH3, CH3. Here also CH3, CH3. So those are the reactions. If we just get double bond is converted into a single bond, and you will get those observations. Then how do we identify halageno alkanes? Same thing. You had read ethanol and you had read silanitrate. Ethanol is used as a co-solvent. So ethanol is mixed both halageno alkanes and silanitrate. So chloroalkane, that means the one which contains chlorine, that will give a white precipitate. Bromoalkanes, that will have a bromine, that will give a cream precipitate. Iodoalkanes will give a yellow precipitate. Right. Then how do we identify alcohols, or in fact the OH group present? To identify the alcohols, we had two tests. One thing is addition of sodium. It gives effervescence of hydrogen. When you had PCl5, it gives steamy fumes of HCl. So two tests to identify alcohols. Addition of PCl5, let's say we have an ROH. Two tests we have. Addition of PCl5, we get HCl, so steamy fumes. Steamy fumes of HCl. Or we can add sodium, that gives effervescence of hydrogen. So those are the two tests we can identify for the alcohols. If it is a tertiary, primary and secondary alcohols, they can further oxidize as well. So when you add acidified dichromate, K2Cr2O7, potassium dichromate, usually alcohols can change the color of dichromate to orange to green. But it doesn't apply for the tertiary alcohols, because tertiary alcohols doesn't ROH. So if it is primary or secondary, right, it changes from orange to green. If a tertiary alcohol is there, which means 3 R groups, if you had acidified K2Cr2O7, right, it doesn't do any change. So it's no change. This is very commonly asked in papers. The most common compound they ask is C4H10O, right? I have taught it earlier as well. C4H10O have 4 isomers, 2 primary, 1 secondary, and 1 tertiary. So C4H10O has 2 isomers, 4 isomers in fact. 2 primary, 1 secondary and 1 tertiary. Both primary and secondary will change the color from orange to green, but the tertiary alcohol, this one, it doesn't change. So it doesn't change the color from orange to green, stay as it is. Right, that's how we identify alcohols. The last part is identification of carboxylic acids. To identify carboxylic acids, we have aldehydes. To identify aldehydes, we have to add silanitrate, ammonical silanitrate, or we call them as tolerance reagent. So when tolerance reagent is added into an aldehyde, it gives a silver mirror. So if we have an aldehyde RCOH, we have commonly 2 tests in unit 3. One thing is tolerance reagent. It gives silver mirror, and the aldehyde gets oxidized into a carboxylic acid. And if you add Fehling's reagent, that is the second one, Fehling's of Redis we say, it gives a brick red precipitate of Cu2O. So those are the 2 tests we commonly use to identify aldehydes. In unit 3 we don't have identification test for a ketone. The last one is carboxylic acid. To identify a carboxylic acid, we have to add sodium carbonate solution. When sodium carbonate or sodium hydrogen carbonate is added into a carboxylic acid, it gives carbon dioxide. So that is a common way we can identify a carboxylic acid. Right? That's a common way that we can identify a carboxylic acid. Right? So there are some other tests they can ask, but those are the common tests they ask in unit 3. So that is how we identify the anions, cations, gases. and few organic compounds, and I put a video of how we can identify them in practically as well. So that's how we do the identification test, right? So if this is helpful, give us a thumbs up and consider subscribing. Thanks for watching.